Hi, this is Professor Verkler from ECE 1220 at the University of Utah, and today we are going to talk about equivalent resistance. Specifically, we are going to learn how to calculate the equivalent resistance for two resistors in series and two resistors in parallel. And then we are going to apply that knowledge to simplify large resistor networks down to a single resistor. First, we'll start with combining resistors in series. So we know that by Ohm's law, V equals IR. And in this case, because they're in series, they have the same current. So that means that V1 is equal to IR1, V2 is equal to IR2, and we know that V0 is equal to V1 plus V2 by KVL, Kirchhoff's voltage law. So therefore, I can write V0 is equal to IR1 plus IR2, because this is V1 and this is V2. And then I can pull out the I, so then in the parentheses I'm left with R1 plus R2. Now in this equivalent circuit over here that performs mathematically equivalently to this circuit, I have V0 is equal to I times R equivalent. Now comparing these two equations, you see that R equivalent must be equal to R1 plus R2. So for resistors in series, their resistances add, and I can replace them with a single resistor with an equivalent resistance, which is the sum of their resistances. Now, we're going to do the same thing for resistors, resistors in parallel. Okay, so resistors in parallel share the same voltage. Therefore, I'm going to write the following equation. I'm going to use KCL to write I0 is equal to I1 plus I2. Then I'm going to replace each of these currents using Ohm's law with V over R. Then over here in the single equivalent resistor case, I have I0 is equal to V over R equivalent. So I would like to look at these in the normal form of Ohm's law, so V equals IR. So let's rewrite both of these. So we have V is equal to I0 R equivalent. And then we have over here, it would be V is equal to, well, let's do a little more algebra up here first. So I'm going to pull out the V, leaving 1 over R1 plus 1 over R2. And then I move that to the other side, so that's going to become 1 over R1 plus 1 over R2. All of that multiplied by I0. Okay, so here we see that these two must then be equivalent. So R equivalent must be 1 over R1 plus 1 over R2. So this is a little more complicated than the series case. And traditionally, you'll see the equation written one of two ways. You might see it written as 1 over R equivalent is equal to 1 over R1 plus 1 over R2. So the reciprocal of the resistances add. And the way I got there from this equation, right, is I multiply 1 plus R1 plus 1 over, 1 over R1 plus 1 over R2, and I multiply that to both sides to get it in the numerator. And then I divide both sides by R equivalent. And that's how I get this form of the equation. The other common form of the equation you might see is if we go and create a common denominator down here. That means I'll multiply this by R2 over R2. I'll multiply this by R1 over R1, which will then lead over here to R2 plus R1 over R2 times by R1. And then when you have a fraction in the denominator like that, you can essentially just, mathematically, you just flip this up to the top. So then that shows that R equivalent is equal to R2 R1 over R2 plus R1. So these are the two standard forms of the equation that people talk about. This one scales, right? So I can keep adding on more and more resistors. This one doesn't scale. Oh, and I'm covering the corner there, so let me move to the side quick. Okay, so in summary, resistors in series add, and here's the equation. Resistors in parallel add by the reciprocal, and the reciprocal of resistance is actually called conductance. Not needed for this course, but maybe good to know in the future if a professor ever referred to conductance in another course. And then for these resistors in parallel, we have something that we call the parallel operator. So when you're showing your math, it's really annoying to have to keep writing out 1 over R1 plus 1 over R2, and so on and so forth. So when we're kind of showing our work on paper, we can use two straight lines like this that are parallel to represent two resistors in parallel and the mathematical operation we would apply to combine them. Okay. So please take 5 seconds, pause this video, and try to figure out the answer to this question. Okay, so as we add more resistors in parallel, we are essentially creating more paths for current. So if we're having more total paths for current, that means more current, holding voltage equal, that is. And so more current, according to Ohm's law, means less resistance, because current and resistance are inversely proportional. And I think I just spelled inversely wrong there. I'm sorry. I am an engineer. Okay, so that means that we expect R equivalent to be less resistance. And it turns out that it's actually less than the smaller of the two resistances, because we have the same current from R1, and then we added another path. So that means that we have even more current than just this one alone, so we have even less resistance. Okay, let us do a worked example. Three ohms in parallel with 6 ohms. And so there are many forms of the equation. You can pick which form you want. I think it's often easiest to work with the one that was R1 times by R2 over R1 plus R2 in this case. So 3 times 6 over 3 plus 6 gives us 18 over 9, which is equal to 2 ohms. So these two resistors in parallel are equivalent to a single resistor of 2 ohms. And then what we're going to continue doing in the next lecture is we're going to practice reducing larger networks using the series and parallel knowledge we have. So for example, these two resistors are in parallel. So I could combine them into one. And then when I replace them with a single resistor, now that single resistor is in series with these other two resistors, so I can add all three of those. And I can rinse and repeat and do that until I'm left with a single resistor. So this is a powerful tool for simplifying more complicated circuits. At this point, I think you are ready to complete your worksheet.